record. Okay. Yeah, I'm starting to record this video and just like usual. Yes. Send your names. So it will be recorded as the. Okay. Yeah, let's just wait a few minutes. I hope everybody is here and we can start. Let's just wait for 1 more minute. Okay. 22 students. Okay, let's start. If there's anyone is trying to attend the meeting, but I am not aware of, please just let me know. I mean, you guys can. I I don't mute all of you guys, so anyone can just to remind me if there's someone trying to attend. Okay. Today we're going to have our lab 2. It's about the vessel stability, or we're discussing about the flotation characteristics of a flat bottom vessel, just like that. I don't know if you guys could see clearly about this one. Basically, just a rectangular shaped pontoon, and with a bridge in here, and you guys could see this is the mast. This is the mast, and with a pendular attached to it. So if we tilting this vessel, the pendulum is going to have an angle. And in the bridge, I don't know if you guys could see it. Let me just grab it. Okay. I think you guys could see it. There are some numbers on it. So which means we have a tilting angle, or we call it listing angle. The pendulum will give us exactly angle, how much degree it's tilting. Okay. And on the front of the vessel, there is a scale. It could tell us how much is the draft, which means if you put it in the water. So you basically just read the numbers in here, so you know how much depth the vessel is submerged into the water. Okay. So what we're gonna do is we start adding weight. You see the two guideposts? I don't know if you can see it. This one. There are two guideposts in here. Whatever you want to add the weight, either the starboard or port side is totally fine. I would just do the starboard. So if I'm doing like 10 gram, yeah, if you add 10 gram, basically you didn't you didn't see it's tilting, or it's relatively small. Let me add a little bit more. So in here, you will have about 2 degree listing. It's not a very obvious, so let me just add more. Okay, right now it's about 5 degree. I mean, it's a very time-consuming experiment because you need to wait until the pendulum is not moving. Okay, right now it's about 5 degree. And for each listing angle, for each tilting angle, we're going to record how much mass we add on one side. Okay, so right now it's about 50 grams. So basically, one tilting angle has a corresponding mass. Right now it's 50, and we just keep adding it. Okay, right now it's 100 gram. Oh, sorry, 100 gram. And the listing angle right now is about 11. Yes, it's about 11 degree. Okay. That's pretty much how we do this experiment. And this is just for one case. We call it case one. Case one is for the empty vessel, which means there is nothing inside the vessel, and this vessel is 3 kilograms. Okay, this empty vessel is 3 kilograms, and we have those ballast weight. Okay, we're going to put inside. Okay, so you will see the difference in the draft, right? Because the vessel is much more heavier. And this is our case two. And what we're gonna do is the exactly same procedure. We just start to add weight to one side. So from now, you will see if the vessel is heavier, you add the same mass on one side. The tilting angle is kind of small, right? Because it's heavier, okay? And we just keep adding weight and record every tilting angle with the mass we add. Okay. For the case three, we got another 2 kilograms. We put in the vessel. Oops, sorry. Okay. And we record the draft again and start adding weight to one side and record everything. So basically, that's how we do this experiment. And I'm gonna move to the explanation of the equations. I think that part is a little bit hard. I better explain very well, or because there are some trigonometry in the calculation. Okay, let me just move this computer. And I hope you guys are already familiar with the procedure of the the experiment is relatively easy. Okay, let me share my screen with you. Okay, we're gonna find out the lab menu. I don't know if I can share it with you guys. Lab menu. This is the lab menu. Up here. Okay. Could you see the lab menu right now?
Yes.
Okay. Oh, yeah, perfect. Okay. So the point 2.2 apparently is basically a discrimination. Sorry, explanation of the device. We have a mass in the middle, the bridge. So we have a list angle scale. Let's see. So in this part, we have some basic information about the vessel, like the depths. The depths, which means the height of this pontoon is 170, 175, and the length width. Also, this one is very important. It called distance from the pontoon center line to the added weight. Uh, so you measure from the middle of the pontoon to the guidepost. We add the weight. Uh, there are some figures better than this. Yes. So this is our x prime. So this location is where we add our weight, and this is the center line. And this distance is useful because we are going to calculate the moment based on this distance. This one is 123, and this is very important. Okay, the mass of empty vessel is 3 kilogram. Okay. Uh, there is some more information about the center of gravity, which is also very important. I will explain it in the equation we're going to talk about. So these numbers will be used in the equation. Okay, so we start from the equation 2.1. I think this one is relatively easy. The F water, which means the buoyancy force. We know the buoyancy force is equal to the weight of the vessel, right? So the vessel MP, the mass of a vessel times gravitational acceleration equal to gamma water times the V displacement, which means the volume of a displaced water. So they should be equal. And the displacement water, the volume of displacement water equal to the height. The H in here is not the height of the pontoon, is the draft. Okay, it means how much the vessel is submerged into the water. So it's a draft. The draft we measured every time we add the bilge weight. At the beginning it's just empty vessel. We have a number and we add 2 kilogram into it, so that our case 2 will have a new draft, and case 3 you have as a new draft too. So in here, the V displacement is equal to the drafts time to the width and the length. Basically, it's the area of the bottom of the vessel, right? Because it's a rectangular shape, so we just do this. So no problem with this equation. And for the equation 2.2, okay, we have a new terminology in here, which is the metacentric height, GM. Um, I don't know how could I show you guys what is the GM. GM is just a terminology in the shipping, uh, especially for the oil and gas industry. We're sailing with the large vessels, and the GM value is very important. We need to calculate the GM value every time when we do like a offshore transportation or something, because we want to know if the vessel is safe enough to sail during the special condition. Like every time we will know the weather report, and we know how much uh, how uh, how let me see, like the wave condition, how big the wave is going to be. So we want to make sure in all the conditions, the GM value is larger than one specific value. Uh, I mean, typically, if the GM is larger than 1, which means the vessel is safe. But if we calculate the GM is less than 1, less than 0, sorry, it's 0. If GM is larger than 0, the vessel is safe. But if the GM is smaller than 0, the vessel is not safe. So for all the basically we're not going to allow the GM less than 0. The GM is, if you can see the figure in here. So basically it means if the vessel has the tilting angle, the center of gravity we call G, and the B is the buoyancy center. Okay. So we extend the center, the vessel center line. Okay, we extend it, use a straight line. Sorry, and we have a new center of gravity because it's tilting. So the center of gravity will be, let me see. No, this is not the center of gravity. Okay, it's not the center of gravity. Center of gravity keeps the same because even the vessel tilting, you know, the center of gravity is still the center of gravity. But for some cases, it's different because if your vessel is it's oil tank, because all the liquid will shift, so the center of gravity will shifting too. But for our case, because the only thing in our experiment is just the empty vessel with the ballast weight, and the ballast weight is been placed in the middle. So it doesn't really matter. So the G is not shifting, but the buoyancy center is shifting. Okay, let me write down something. Okay, we all know the B in here. The B is the buoyancy center, and the B is coincide with the centroid of the submerged part. So it's this part. Okay. So because the B is in here, so the how we calculate the EB basically is 2 over H. Okay, 2 over H. This is H, the draft, and the EB is 2 over H because it's the in the middle. And if our submerged part become a trapezoidal shape like this, the B is going to shift, right? The B, well, from the beginning is located in here, and it will switch.
Excuse me, I think somebody needs to be connected again. They got disconnected.
Okay, yeah,
Nikki,
thank you.
you're welcome.
So if we are able to find this one, okay, right? I think, yeah, it's basically for me how we calculate the new center of a buoyancy. We just, for me, I would just, you know, cut this trapezoidal shape into a triangle and into a rectangular shape, and find its own center of, find its own centroid, and use the information to find the new. I don't know why Nikki is disconnected again. Okay, so once we have a new B, okay, which is the resultant force of the buoyancy force, we just extend use the vertical line going up, and this line's from the center line. Okay, so we will have an we have a intercept point M in here. So GM is our value. We want to calculate this GM. For some cases, the M is below the G, okay? For some cases, the M could be below G. So in that case, the GM is a negative value, which means the vessel is not stable and not safe, has the possibility of capsizing. So which means if it's tilting, the restoring moment cannot make the vessel back to its original position. It's going to capsizing. So every time we want to make sure that the GM value is larger than 0, which means the M, the metacentric the metacentric value is larger than 0. Okay. Let me remove all the marks. Okay, and just remember this one is our theoretical equation for the GM. And what we're gonna do is we have our equation to calculate the experimental value of the GM, and we compare each other. For each case, we have a theoretical GM value. Okay, let me explain this equation. IO is the in here. Okay, it's a second moment of the water line about the axis passing through a region. The equation is given. The IO equal to L W cubic over 12. I think you guys are familiar with it. So the L is the length of the vessel, the omega or W, whatever. Cubic is the width of the vessel. Okay, so from here we know L is 380, omega is 250. Okay, so this part you know it. Okay, so the displacement are all I already explained. So it's the draft times the width times the length. Okay, so this part no problem. And what is BG? BG is from the buoyancy center to the center of gravity. Okay, so from the figure we can see we want to know the BG, right? We want to know the BG, and the BG is equal to EG minus EB, and we know the EB is just H over 2. Okay, so that's we calculate the centroid of the submerged part. Okay, so it's easy. Once we know that, and here's the tricky part. We have our EG in here. So let me explain this. The EG, you want to calculate the center of gravity of the vessel. You have to know exactly how what is the weight distribution. So basically, this equation is how we calculate the center of gravity based on the weight distribution. So for the case 1, let me use this. Okay, for case 1, because we have an empty vessel and we know the empty vessel is 3 kilogram. Okay. So there is no this part. We just neglect this part. We want to know the XP. How much is XP? XP is given in the previous sections. And this WP is the weight of the empty vessel. And the WBI is the bilge weight, or we call it ballast weight. So we only need to use this part in case 2 and case 3. In case 2 is 2 kilogram, and case 3 is a 4 kilogram. So we need to change this part. So every different cases, the EG is different, but the EB, you're going to use the same equation, and the BG use the same equation too. Okay. Let me find. Okay, you guys could see the center of gravity of the unweighted vessel, XP equal to 125. Okay, that's for case 1. XP is 125, which means from the bottom of the vessel, the center of gravity of the empty vessel is located. Sorry?
No, sorry.
Okay. Okay. So so for the empty vessel, the center of gravity is located 125 millimeter above the bottom of the ponton. Okay. So in this equation, So in this equation, the WP, is 9.81 if we use the SI unit times 3 kilogram. Okay, that's the weight of the vessel. And XP is 125 millimeter over WP. So basically means EG is equal to 125 millimeter for the case 1. Because we are not adding any bilge weight already. So in case 1, there's no this part. But for case 2, let's check the value over here. The center of gravity of the 2 kilogram bilge weight XB1 equal to 30 millimeter. Okay, so for I would just talk about the case 2, and I'm not going to talk about the case 3 because it's the same. We just apply this number. XB2 means for case 3, and XB1 means for case 2. Okay, the XB1 is 30 millimeter. Okay, so in this equation, it's going to change. Okay, so this part is the same, right? It doesn't change. So for the case 2, I better have a pen. Okay, so it's still, the equation is equal to 9.81 times 3 plus, okay, the bilge weight in case 2 is 2 kilogram times 9.8 times, okay, this part, sorry, I forgot to add this 125. Okay, that's the XP. XP is 125. And XBI, okay, XBI is XB1 because it's case 2, we are using XB1. And for case 3, we are going to use XB2. So it's 30 millimeter, okay, for case 2. And over WP, right? WP is this part plus WBI is this part. Okay, we just add this part together. So we are able to find what is the center of gravity. I think that's the basic, right? That's something basic. I don't know. You have already know in some other classes. That's how we calculate, because for the empty vessel is like kind of in the middle, and the bilge weight is kind of in the bottom, right? So that's why XB1 is 30 millimeter, because it's really the center of gravity of the bilge weight is really close to the bottom of the vessel. So we measured it already. It's a 30 millimeter from the bottom. It's for the bilge weight, 2 kilo bilge weight, and for the empty vessel, it's in the middle. So using this equation, we're going to calculate a center of gravity. Basically, it's in the somewhere between 125 and 30. Okay. Well, it's going to end my meeting in 10 minutes. Okay, let me just accelerate. And everything I'm talking about today, I will have a hand note together with the data sent to the Blackboard. So if you're not completely understand what I'm talking about, you can read the menu again and come back to see my notes. So it's totally fine. Or just shoot me an email about your problem. Okay, so you know how to calculate the EB and the EG, you will get the BG in here. So basically that's everything about the theoretical theoretical value of the GM value, okay? So from the equation 2.2 to 2.6, we're able to calculate the theoretical value of the GM. And from the equation 2.7 to 2.10, we're going to calculate the GM value, experimental GM value. And there are some trigonometry stuff. Let me see. So we're taking a moment to the center of gravity. Let me see. FBGG, FPRA. Okay. So in this figure, the whole vessel is rotating with its center of gravity. Okay. If we want to take a moment of the center of gravity, so you see the FP in here. The FP is the G times the mass we added to the side of the vessel. Okay. So once we got the FP, because FP is given, and RA, see, RA here. Basically, if we use a straight line, vertical line passing through the center of gravity, so RA is our arm, right? Use the force times the arm gives the moment. Okay, this is a clockwise moment, trying to tilt this vessel. And we have our buoyancy force in here, because if it's tilting, the buoyancy is a switch. The buoyancy center is a switch. So the FB is the resultant force. Okay, the center of a, we can call it the center of a pressure, or the location of the resultant force, buoyancy force. So GG is the arm of this force. So the arm times the force giving a counterclockwise movement. So they will be balanced. Okay. So from this equation, the balance the moment equilibrium, we can derive our final equations in here. So I don't know if I can finish this meeting. If I cannot finish in 5 seconds, please, I will open another one, and please just attend the meeting again. Okay. Okay. So here the equation 2.8 is let us know how we calculate the GG. Okay. The GG is in here, and this is our GM. Okay. And the listing angle is here. So we know the GG prime over GM is sine theta. Okay. It's a sine theta. Theta is a listing angle. So we have the equation like this. In RA is the arm of the added mass, the force caused by the added mass. So this one is equal to HA cosine theta plus HG sine theta. I'm not going to talk too much about this. So basically it's just trigonometry stuff, and we need to figure out. So in here, HA, okay, we just take this part. HA cosine theta. HA, what is HA? HA is from the center line to the point of the force. And this one is given. It's 123. I think I mentioned before in section 2.2. Okay, it's the distance from the pontoon center line to the added weight. So x prime is the HA equal to 123. Okay, so we have the HA, we have the cosine theta, and we have the sine theta. So the only thing we don't know is the HG in here. Okay, what is HG? HG is from the center of gravity to the top of the pontoon. Okay, so we don't know this distance, but we know the depths. Okay, the depths of the vessel. Okay, we know this depth. The depth is 175. Okay, and we use we just calculate the HG. Sorry. We just calculate the HG using the equation HG equal to 175 minus EG. Okay. Let me move it here. So the HG is equal to 175 minus EG, and the equation of EG is in here. Okay, when we calculate the theoretical value of GM, already know the value of EG, so we are able to calculate the HG. So in the final equation, the only thing we need to know, the GM value is equal to FP times RA, and you're able to calculate RA using equation 2.9. And the W is the weight of the vessel. So for the case one empty vessel is just the G times 3 kilogram. For the case 2 is we add 2 kilograms, so it will be G times 5 kilogram. And for case 3 we add 4, so it's basically G times 7. Okay, so for each case this W is changing. Okay, RA is changing, and the theta is just the listing angle. Okay, so the GM value for each case, it's a line. Okay, it's a data set. It's not a it's not a value. Okay, it's not a single value. For the GM theoretical, it's a single value, but for the GM experimental, it's a line. Okay, I think I finished the explanation of the equations in here, and probably I will. Yeah, I need to talk a little bit more about the data analysis. Yeah, I only have 1 minute, and yeah, I only got 1 minute and 30 seconds. So probably I would just close this meeting, and I will reopen it because it's very important. I don't want cause any confusion about how much figures you want to have. You need to have in the report. Okay, so I'm going to close this this meeting and open another one. So please just come back. Okay.